In this video, we'll understand what is the difference between Fermat's theorem and Euler's theorem. So before that, we have to understand what is Euler's phi function, denoted as phi of n, or it is also called totient function. So phi of n is an integer which gives you the count of numbers which are relatively prime to n and also less than n. So for example, when n is 4, phi of 4 is 2. So you can see the numbers which are less than 4 are 1, 2 and 3. So 2 is skipped here because 2 is not relatively prime to 4. Only 1 and 3 are relatively prime to 4. So phi of 4 is 2. If n is 5, then the Euler's totient of 5 is 4 because the numbers which are less than 5 are 1, 2, 3 and 5. All of them are relatively prime to 5. So the count is 4 here. If the numbers are small, we can actually list them out, but as n increases, we have a method to calculate phi of n. First step is n should be written as the product of prime factors like this: p1 to the power some power k1, p2 to the power k2 and so on. And phi of n is calculated by n into 1 minus 1 by p1 into 1 minus 1 by p2 and so on. In this example, say n is 20. First we write it as product of prime factors. So prime factors are 2 and 5. So p1 is 2, p2 is 5. So phi of n, which is phi of 20, is n into n is 20, 1 minus 1 by p1, p1 is 2, into 1 minus 1 by p2. And this gives you the number 8. Now what are these 8 numbers which are less than 20 and also relatively prime to 20? So these are the 8 numbers: 1, 3, 7, 9, 11, 13, 17 and 19. When n is prime number, for example 19, its prime factors are 1 and 19 only. So phi of 19 is 19 into 1 minus 1 by p1. p1 is 90. So it gives the count as 18, which is just 1 less than the given number. So it is n minus 1. So when n is prime, it is very easy to find out phi of n. For example, you take this big number. You can notice this is a prime number. So phi of this number is just 1 less than this, that is n minus 1. So phi of 21,377 is 21,376. Now we'll see what is Euler's theorem. Euler's theorem is a power phi of n is congruent to 1 mod n. The conditions are a and n should be relatively prime and n should be greater than or equal to 1. For example, 3 square is congruent to 1 mod n because 3 and 4 are relatively prime and n is greater than 4. And phi of 4 is 2. So 3 square is congruent to 1 mod 4. And that is true because 3 square is 9. 9 is divided by 4 gives the remainder as 1. Now next is Fermat's theorem. Fermat's theorem is a special case of Euler's theorem. Here there is no condition on n. N can be prime or non-prime number also, composite number also. But in case of Fermat's theorem, this n has to be a prime number and a and p should be relatively prime. So a to the power p minus 1 is always congruent to 1 mod p. This is Fermat's theorem. Because when n is prime, its Euler's totient will be n minus 1. So that is what we are getting it as Fermat's theorem. For example, 3 power 4 is congruent to 1 mod 5. Now 3 and 5 are relatively prime. 5 is a prime number. So by Fermat's theorem I can write 3 to the power 5 minus 1, which is 4, is congruent to 1 mod 5. Now same thing, if you apply Euler's theorem, n is 5 and Euler's quotient of 5 is 5 of n is 5 minus 1, which is 4. Even that gives you the same value, 3 power 4 congruent to 1 mod 5. So here I show you few examples where sometimes we cannot apply Fermat's theorem, sometimes we cannot apply both Fermat's and Euler's theorem, but modular exponential method we can use. In this example, find the remainder when 2 to the power 2023 is divided by 7. So let us take a as 2, n as 7, or p. So a is 2, p is 7. We try to solve it by Fermat's theorem. So p is 7, which is prime. And GCD of 2 and 7 is 1 because they are relatively prime. And by Fermat's theorem, a to the power p minus 1 must be congruent to 1 mod p. A is 2. 2 to the power p minus 1 is 6. That is congruent to 1 mod p, which is 7. So 2023 divided by 6 gives the remainder as 1. So first we raise 2 power 6 to the power 337 and then multiply it by 2 to the power 1, both sides. So this left side becomes 2 to the power 2023 and here only 2. That gives you the remainder as 2. The same problem can be solved by Euler's theorem. A is 2, n is 7 and 2 and 7 are relatively prime. Next we have to calculate phi of n. So phi of 7 is n minus 1 because n is prime number, it is 6. So a power phi of n must be congruent to 1 mod n as per Euler's theorem. So 2 power 6 is congruent to 1 mod 7. Same procedure as Fermat's theorem, even this gives the remainder as 2. Next one is modular exponentiation method. So here we choose the small power of 2 so that we get a small remainder here. 2 cube is 8. 8 divided by 7 leaves the remainder as 1. So when 2023 divided by 3, it gives the remainder as 1. So 2023 can be written as 3 into 674 plus 1. So 2 cube must be raised to 674 and 1 to the power 674, which gives only 1 here. Left side we get 2 to the power 2022, but we want here 23, so both sides multiply by 2. So 2 to the power 2023 is congruent to 2 mod 7. It means 2 is the remainder. So in all these three methods, we got the same remainder as 2. Now consider another example. Find the remainder when the same number 2 to the power 2023 is divided by 15. So a is 2 here, n is 15. We cannot apply here Fermat's theorem because this is not a prime number. We can try with Euler's theorem. So for that we have to calculate phi of 15. The prime factors of 15 are 3 and 5. So P1 is 3, P2 is 2 and phi of 15 is 15 into 1 minus 1 by P1 into 1 minus 1 by P2, and that gives the count as 8. So now we apply Euler's theorem. A to the power phi of n is congruent to 1 mod n. So a to the power phi of n is 8. is congruent to 1 mod 15. So from 8 we have to get 2023. For that we divide 2023 by 8, and it can be represented as 8 into 252 plus 7. So 2 power 8 to the power 252 is congruent to 1 to the power 252 mod 15. Both sides we have multiplied by 2 power 7. So here we get 2 power 2023, which is congruent to 2 power 7, which is a small number. When divided by 15 gives the remainder as 8. We can also use modular exponent method. So we try with a small power of 2 so that we get a small remainder here. 2 power 4 is 16. 16 divided by 15 gives the remainder as 1. So 2 power 4 is raised to 505, both sides, here and here. So, and then multiply both sides by 2q, so that it becomes 2 to the power 2023, and right side is 2q, which is 8 mod 15. So the remainder is 8. So both give the same remainder, but Fermat's theorem cannot be applied here because the modular value is not prime number. Find the remainder when 123 to the power 6 is divided by 29. So what we notice here is the base is large but the exponent is small. If we want to apply Fermat's theorem, this is P, which is prime, okay, and 123 is A. 123 and 29 are relatively prime, so both the conditions are true. Next, when we apply the Fermat's theorem, A power P minus 1 congruent to 1 mod P, it becomes 123 to the power P minus 1, that is 28 is congruent to 1 mod 29. But we want here only 6. Here it is larger, 28. So we don't use the Fermat's theorem. Same is the case with Euler's theorem. So A is 123. This is A. This is N. And they are relatively prime. So for 29 we have to calculate phi of n. 29 is a prime number, so phi of n is n minus 1, so it becomes 28. Phi of n is 28. So A power phi of n, that is 123 to the power 28, is congruent to 1 mod 29. So here also the power is larger than the required one. So both theorems are not applicable. We try with the exponent method. So 123 when divided by 29 gives the remainder as 7. Both sides raise it to the power 6. So 123 to the power 6 is congruent to 7 power 6 mod 29, which is a small number. You can use calculator and divide it by 29. The remainder will be 25. Okay. Thank you for watching.